Hello, and welcome to the second in a series of video lectures introducing a second course in string theory. In this lecture, we'll talk about Chapter 2 of the notes on superstrings. We assume that you already have a working knowledge of bosonic string theory, for example from David Tong's excellent lecture notes. The chapter is split into 4 subsections. Firstly, we introduce the Rns action. This is the gauge-fixed form of a string action with local worldsheet supersymmetry. The action takes the following form. As usual, it's proportional to the string tension, or 1 over the parameter alpha prime, and we integrate over the 2 string worldsheet coordinates. The first term looks like a Nambu-Goto string action, exactly as for the bosonic string. And the second term looks like several Majorana fermions, where the gammas are the two-dimensional gamma matrices. This is the starting point for the quantization of the superstring. But it's not at all obvious that it gives you a theory with space-time supersymmetry. In fact, the easiest way to show that this gives you a theory with space-time supersymmetry is to recast the action into Green-Schwarz form, where the space-time supersymmetry is manifest. This sadly goes beyond the scope of the course. In the second section, we examine the boundary conditions on a superstring by varying the string action and requiring it to be 0 for configurations obeying the equations of motion. For the bosonic string, we get the famous boundary requirement that the integral between the initial and final worldsheet times of x prime delta x evaluated at sigma is 0 and sigma is pi must vanish. And this leads to the usual closed and open string division and the familiar identification of Neumann and Dirichlet boundary conditions in the open string case. So that's the bosonic case, but what about the superstring? For the superstring, we get an additional term which must vanish, which looks like the following. Psi bar mu, gamma 1, delta psi mu, evaluated at the string endpoint sigma is 0 and sigma is pi. This condition gives you the oft quoted Ramond and Naveau-Schwarz boundary conditions on an open string, often known as R and NS for short. In the third section of the notes, we discuss constraints which must be placed on the superstring in order to get a consistent theory. These effectively arise from the gauge symmetry of the non-gauge fixed theory. In the non-gauge fixed theory, there are Lagrange multipliers that we must take into account. And it is these Lagrange multipliers that provide the constraints. In the case of the superstring, there are two classes of constraints. First, the familiar constraint on t++ and t minus, the components of the stress tensor in light cone coordinates must vanish. And secondly, a similar constraint on j++ and j minus, where j is the worldsheet supersymmetry current. These must be taken into account to obtain a well-defined spectrum without negative norm states when we quantize. The final section of the superstring notes considers the spectrum after quantization. This is quite involved, but is clearly detailed in the lecture notes themselves. Importantly, by taking into account the boundary conditions, we end up with various different types of superstring theory called type 1, type 2a, and type 2b. These have subtly different field content. In this section, various other important concepts are discussed, not least the idea of GSO projection, which allows one to consistently obtain a supersymmetric spectrum. It turns out that this is not an ad hoc procedure. In fact, it emerges from a one-loop consistency condition. At this point, I recommend that you take a careful look at the notes where there's much more detail on all the topics we've discussed. Thank you for listening.